So that's good. I thought that there was a... Okay, so last time we were talking about anions and cations. Well, we hadn't gotten to cations yet, but anions acting like conjugate bases. So particularly, well, any anion could technically be a conjugate base, because if it's an anion, that means it can add a hydrogen to it, because hydrogens have positive charges. So not everything will act like a conjugate base or make a solution basic because it's absorbing hydrogens. So which of these anions acts as a weak base? Huh? C. Who said C? Oh, what flavor do you want? Do you not care? Oh, grape. Grape. People like grape. It is C. Incorrect answers also get Jolly Ranchers. I just want you guys to answer. Now, all right. I realize I just created a problem because you might just say anything. That will not get a Jolly. Like, good effort here. Try to answer the question. Yeah, so fluoride here. And I think the key to this is always thinking about, well, what if I added the hydrogen to it? And really thinking about, especially for acids, is that going to be a strong acid? Hydrofluoric acid is not a strong acid, it's a weak acid. And if this is a weak acid, then this is going to be a weak base. Now these other ones are strong, which means that they are going to be neutral, right? HCl, HBr. And that's because they're really like such weak bases that like they just don't even act like a base at all. Like we did the whole thing where I showed you like the Ka, and then if we flipped it, what that K would be for the reverse, and it's super teeny tiny. So we don't even consider them to be bases, they're just neutral. So they wouldn't have any effect. When we move on to cations, cations can sometimes act as weak acids. There's three categories. Well, pH neutral. So strong bases dissociate completely. So things like calcium, sodium, and potassium. When they ionize completely. They get rid of the hydroxides, and that's it. Nothing else happens there. So the counterions don't ionize the water. Those are the easy ones. I think the next category is not too hard either. And again, sort of the reverse, think about adding hydroxide to these. So if it's calcium hydroxide, that's a strong base. Sodium hydroxide, strong base. Potassium hydroxide, strong base. They all ionize completely. Our other cations are conjugate acids of weak bases. So here, like the base, B is just base. So adding a hydrogen to it gives it a positive charge. Bless you, bless you. And so when we add that to water without its, I guess, without the base, it'll act as an acid. So it'll lose some of these. It'll be a weak. It's like if this is a weak base, then this is going to be a weak acid. So a cation is the conjugate acid of a weak base is a weak acid. And actually, in this case, you kind of think about looking at the compound, can I remove a hydrogen from it and get a weak base? So just off the top of my head, NH4 plus is one of those. I can remove a hydrogen. Minus a hydrogen gives me NH3, that's ammonia, that's a weak base. So NH4 plus is going to be a weak acid. So the next ones that are weird? Yeah. This next category is kind of weird. It has to do with complex ions. So things with positive charges, things with, so yeah, the first one was basically positive charges. These are all cations, right? The strong bases, counter ions of strong bases, they ionize completely. The conjugate acids of weak bases will act like weak acids. And then we have these small, highly charged metals. And they do kind of a weird thing. So when you add them to water, they will hydrate. They're called hydrates because we're adding water, so the water is complexing with the aluminum and arranging itself more permanently than just sort of being dissolved. And when you do this, because that aluminum has such a high charge, it's pulling in a lot of electron density. One of the hydrogens on the oxygens can be lost to a water. So we convert one of our waters into, so this goes from 6 to 5, and then we convert it into a hydroxide. Because the electrons are being pulled so tightly into the highly charged aluminum that the oxygen doesn't have enough electron, or the oxygen from one of the waters doesn't have enough electrons to hold on to that hydrogen very tightly. So what does it mean by small, highly charged metals? Where would you think that is on the periodic table? I mean, that's where aluminum is. Oh, yeah. They get smaller as we go across. Oh, what flavor do you want? Okay. Oh, sorry. There you get two. I've got so many. Yeah, so maybe more towards the right. What's the other periodic trend for size? For like charges? What about for size? Right, increase is going down. You answered, so you get a, what flavor do you want? Yeah. Okay. Oh, hard to reach back there. You guys should sit closer to the front.
This one would be like the top and the right. So
Yeah.
The transition metals, and then to the right.
So top of the transition metals, and then farther towards the right. So at least for this class, there aren't, actually I looked on Alex, I don't think there were any questions about this. So like not even that I didn't assign any, I couldn't find any. Or actually there was one that pops up a little bit. I think they just do iron and aluminum. I didn't go through enough to check, but first row, say first row transition metals and aluminum. Oh, Julie, did you want what flavor? Doesn't matter. Yeah, so think of these as like the first row transition metals. That's where you're probably going to find this. Yeah, more towards the right, but like iron is another one that does this a lot, at least in the Fe3 plus. And it's kind of in the middle of the transition metals. So the left or right, not as important as the top to bottom. And if you want to get really specific, I would say probably higher oxidation states of those first row transition metals. So iron 2 plus, Probably not. Iron 3+, yes. The book does not go into more detail. All right. Determine whether a cation is acidic or pH neutral. Lithium. Think about it a little bit. So if lithium was a base, what would it be? It would be a strong base. Who said that? Do you want another one? Oh, sorry. I wanted to miss high, I don't want to hit somebody. All right, yes, lithium would be a strong base, right? If we add a hydroxide to it, that's a strong base. So this would be weak acid or pH neutral? Neutral. Oh man, a bunch of people answered at the same time. It's neutral. Guess we should move to raising hands or something. How about B? If I actually think about this one, do I add a hydroxide to this or do I remove a proton? Remove a proton, remove a hydrogen. You can't kind of think of it as like if you added NH3, or sorry, well, in this case it's NH3, but like NH4OH becomes NH3 and H2O, so like one of these hydrogens leaves with the oxygen. And in general, like anything that's got like carbon and hydrogens, or carbons and then a hydrogen, is going to be basically ammonia, ammonium. So this, when we think about when we remove a proton, NH2 no longer has a charge. That would be a weak base. This would be a weak acid. And then iron 3+.
Weak acid.
Weak acid. Doesn't matter. It is a weak acid because first row transition metal, iron, highly charged, 3+. So this would complex. And so you do just kind of need to remember that. And so it's going to be a weak acid. Because it's going to pull in a bunch of waters, then one of those waters loses the hydrogen, and that's what makes it an acid. Multi-step process. So when we go through these, or when you get problems like this, where you have a cation and an anion, essentially you just have to separate the two and think about them sort of one at a time. Go through the cation. Is the cation going to be slightly acidic, slightly basic, or neutral? Is the anion going to be slightly acidic, slightly basic, slightly neutral? Most of the time, one of them will be neutral, the other will not. Or they'll both be neutral. So in this case, our first case here is salts in which neither cation nor anion acts as an acid or base. So really what we're saying is the cation is neutral and the anion is also neutral. Second sort of easy case is where you look at either of them and the anion acts as a base to form a basic solution, but the cation is neutral. So cation is neutral. anion is a weak base. So anion is a conjugate acid of a weak base. Oh wait, or a conjugate base of a weak acid, so it acts like a weak base. So again, just split it apart. Cation, anion. Is one of them neutral? Look at the other one. So what do you think the third category is going to be?
Neutral anion.
Yeah, neutral anion, acidic cation. Do you want another one?
Sure.
Oh, there. Stuck the landing. Yeah. So the next one is salts in which the cation acts as an acid, but the base is, or the anion is neutral. Is a weak acid. Anion is neutral. Things don't really get more complicated than that. The trick, though, is to separate the two. Like, don't try to think of the whole thing all at once. Rewrite it as separate things. So like in all of these, like the iron 3+ and a Cl minus. Cl minus, if it was an acid, would be a strong acid, so it's going to be neutral. Iron 3+ is a first row transition metal with a high charge, so it's going to be slightly acidic. So then the last category, of course, is where we have to make everything a little bit more difficult, not too difficult. But what if they both act as something? So the cation is a weak acid, the anion is a weak base. Really, you just compare K values. So you do need to know what the Ka and the Kb are. Sorry, I was thinking about on a test. I think I would give you all Kas and Kbs. But what we're talking about here is the conjugates of a weak acid or a weak base. Okay, so audio is going to sound a little different here because I'm recording this in my office. There was a lot of confusion, I think, about this slide 80. I did all of this example up here, which now being cut, don't worry about this. We're going to do another replacement example here just to try and make everything more clear. So, is the solution acidic, basic, or neutral? So we have this solution, ammonium nitrite. The first thing we need to do when we're looking at any salt is break it up into the different ions. So we got NH4+ and NO2-. Now I'm looking to see if these are conjugates of something that is going to be a weak acid or a weak base. Now NH4+, that one should be familiar, like ammonium hydroxide. So this is the conjugate of ammonia. So NH4+, it's going to be our conjugate of ammonia, NH3, and NO2-, that's the conjugate of HNO2, which is nitrous acid. So we've got this is a weak base, this is a weak acid, which means that my original compounds up here are conjugates of weak acid, weak base. So NH4+, that's also going to be a weak acid, and NO2- is going to be a weak base. So now I've determined this is going to be a weak acid. This is going to be a weak base. So this is the tricky situation, and this is why I wanted to do an example, because if I have a weak acid and I have a weak base, well, which one is the stronger weak acid or the stronger weak base? Whichever one has the larger Ka, smaller negative exponent, is going to be stronger. So I'm not expecting you to memorize these, so you might go look them up on a table. So over here I've got a table, but these tables, which are pulled from the textbook, these tables don't have they don't have NO2 minus. They don't have NH4 plus. Oh, maybe I should swap these. Right, this here, like, because that's an acid, that's a base. Top one's acids, the bottom's bases. I don't know, like, they're not on there. The reason I wrote them up here originally is because these are conjugates of what are typically thought of as weak acids or weak bases. So I'm not looking for nitrite. I'm actually looking for nitrous acid. And now nitrous acid has a Ka value, but that's for the nitrous acid. So my Ka value there is 4.6 times 10 to the negative 4. So HNO2 Ka 4.6 times 10 to the negative 4. And then down on my bases table is where I'll find what I'm looking for the ammonia. So this is ammonia. This is ammonia. Sorry, this is ammonium down here. But I'm looking for ammonia, which is its conjugate base. And that's 1.76 times 10 to the negative 5. To come up here. And now I can write this down, NH3, but that's a Kb. 1.76 times 10 to the negative 5. Okay, so the problem then is this is a Ka. But I want to know, for the weak base that I have, what is the Kb? So we actually don't need, just going to cover these up. All right, we use that information. What I really need and what I want to compare is for my weak base, what is its Kb? For my weak acid, what is its Ka? So to find those, I can use Ka of nitrous acid to find Kb of nitrite. We do need to use the fact that, maybe I should rewrite these over here. Let me move this over, right? Okay. So problem is that these are Ka and Kb. I need to now convert them. So I need to convert my Ka into a Kb. Oops. And I can do that with Kw equals Ka times Kb. Because Kw is always 10 to the minus 14. That's the autoionization of water. And that equals 4.6 times 10 to the negative 4 times whatever the Kb would be, or which is what I'm looking for here. Negative 14 divided by 4.6 e to the negative 4. So my Ka, or my Kb here is 2.17 times 10 to the negative 11 equals Kb. So that's a pretty small Kb. And then over here, I'm essentially doing the same thing. I can use the same expression. Kw equals Ka times Kb. Kw is 10 to the minus 14 equals, now I have a Kb, so this is going to be Ka times my Kb. Great. And now it's 10 raised to the negative 14 divided by 1.76 e to the negative 5. So 5.68 times 10 to the negative 10 equals Ka. And then I got to look at which one of these is larger. They're both very, very small. But this is 10 to the minus 10. This is the larger of the two, comparing the Ka to the Kb, which means that this will be solution is slightly acidic. So the point here being really that in order to solve this problem, I need to look at a table of values, and the tables are usually not going to have the salt that I'm looking for, or the conjugate of what is usually an acid, or the conjugate of what is usually a base. But what I can look for is the base. So NH4 plus is the conjugate acid of NH3. NO2 minus is the conjugate base of HNO2, or nitrous acid. So I can use these values to find Ka and Kb and Ka, so that I can compare those values and figure out which one is going to dominate and make my solution acidic or basic. Okay. So if we're looking at just this, we have this problem. The question is this solution going to be acidic or basic? So we separate the ions. We say, okay, is NH4 plus the conjugate acid of a weak base? Yes. It's the conjugate base, or it's the conjugate acid of NH3. So then I would need to go and look up what is the Kb for NH3? Kb for NH3. And then I would say, is NO2 minus the conjugate base of a weak acid? In this case, yes, nitrous acid. So then I go and I look up the Ka for nitrous acid. So these are for the conjugates. I can't compare them for this problem. So you have to convert them into... So really what I want to know is, what is the Ka for this? What is the Kb for this? And to get that, I will take... Well, we could do some color coding. All right, so this. I'll do, because I know that Kw equals Ka times Kb, then Kw divided by Kb will give me the Ka. Kw divided by Ka would be Kb. And it'll be Kb for this one. Cool. Everybody tracking so far? So when I do that math, because Kw is the same thing, this is 10 to the minus 14 divided by 2.4 times 10 to the negative 7. That's going to give me, which I didn't actually write down. Oh, I have it on my calculator still. This is Ka equals 3.125 times 10 to the negative 10. And this one is going to be 10 to the minus 14 divided by 3.2 times 10 to the negative 5, which means my Kb for that is, what did I say, to 8? Yeah, 4.2 times 10 to the negative 8. And now I can compare the conjugates of the Ka and Kb of my conjugates, which is what I actually have in this problem. And you can see that even though NH3 was smaller up here, now over here, Oh shoot, I wrote them backwards, didn't I? Yeah, I wrote them backwards. Yep. Okay, sorry, I reversed them. So even though KB was smaller up here, it is now larger. Its Ka is larger than the KB for the nitrite. It's not even that they're just the reverse. And this is another, I mean, this is a good thing to recap. Like, why do we need to do this equation, Kw equals Ka times Kb? Because when we've just reversed reactions before, you just do, take the K to the negative. We're not doing exactly that here, because the equation for like Kb is going to be NH3 plus, not H3, H2O is going to give me NH4 plus OH minus. But the equation for Ka is the acid also plus water, which gives me NH3 plus H3O plus. So Ka and Kb are not the reverse of each other. They're the conjugate reacting with water. So this would be the equation for, get rid of these. This is the equation for Kb, this is the equation for Ka. If I add them together, I get H2O plus H2O is OH minus plus H3O plus, which is the equation for Kw. So Ka times Kb equals Kw. Well, now there's definitely going to be one of these on the next test. You're just comparing Kas and Kbs. It took me 3 tries to make up a problem.
Okay, and then the overall solution is more acidic. Because
The Ka is. Yeah. And yeah, actually, most of that was coming up with 3 different examples. But I kept writing them on top of each other, which makes it all so confusing. I should probably delete that previous part in the video and just have this part. That way, when you go and rewatch it, hopefully you rewatch it, you're like, oh, okay, that was the only explanation that mattered. This part on this page for how you compare them. Are there any questions? Okay. There is a nice table that summarizes all of this. Although this is probably just because I've done it enough, but like I don't know if you really need a table because, again, you're compare cat or like check the cation. And you check the anion. If one of them is neutral, actually, if both of them are neutral, let's read through this table. Counterion of a strong base, conjugate base of a strong acid, which means they're both neutral, so it's just neutral. So then everything in this column is dependent on what the cation is. And actually for cations, If it is anything at all other than neutral, it's going to be slightly acidic. So if my anion is neutral, then all I care about is the conjugate acid. Along the bottom here, this is if the cation is neutral, then all I care about is the anion, and the anion is going to be basic if it's the conjugate of a weak acid. And then if both of them are conjugates of a weak acid and of a weak base, or a small highly charged ion, then it just depends on the relative strengths. In which case, I would provide to you K values. Probably provide you K values in a table on like the back of the exam, so it doesn't just completely give away what type of problem it is. But then you just have to compare those K values. So that was the long and the long of it. There is an Alex problem that practices this, and you can get really fast at them, because once you've seen a bunch of them, you get really quick at recognizing like, oh, that's the conjugate of a weak acid, or that's the conjugate of a weak base, or that's a small highly charged ion. And I would encourage you to it doesn't take that long, because you can just keep pulling up new ones. Just do that until you get quick. There might not even be an Alex problem that has you compare them. Oh, we'll see if I even remember. Cool. Now we can put this into practice a little bit. Are there any on here that are? No. Okay. So again, compare the cation and the anion. So what's my cation for A? Na plus. You're going to have a dragon's horde of Jolly Ranchers. Do you want another Jolly Rancher?
I won't make you do this every day. It's only novel.
Oh, sorry. Brought it over there and I just dropped it on the ground. Okay. And then the anion would be the other HCO3 minus. So is the cation?
The cation is the conjugate of a strong base.
Yeah, sodium hydroxide, strong base. So I don't care about the cation because it's neutral. But the base, or the anion, I should say, HCO3, again, add a proton to it. H2CO3, is that a weak acid? Yes. Then my conjugate is a weak base. So this is a base. So this solution is basic. Do you want a Jolly Rancher? You have a preference on flavor? Uh-huh. All right, next one. Do I ask the easy one or the hard one first? What's the cation?
CH3, CH2, NH3.
Plus. Deal minus. Do another Jolly Rancher? Telling you, I got 5 pounds, and it didn't cost very much. Let's start calling on people, maybe make it more fair. Okay, so Cl minus, conjugate of a strong acid, it's a neutral. You could do this. Somebody new this time. Is CH3CH2 NH3 plus the conjugate acid of a weak base? has carbons, it has nitrogen. So it's basically the conjugate of NH3, NH4 plus. So this is a conjugate of a weak base. So this is a weak acid. So that solution will be acidic. Jolly Rancher for me. All right, potassium nitrate. K plus, NO3 minus. Is potassium the conjugate of a weak anything? No. So that's neutral. What about nitrate? Also neutral. So the solution is a green apple at the top. Sorry, I was just wondering about the distribution of flavors. Like, is it even? Iron nitrate. What's the conjugate? I guess what's the cation? 3 plus. And the anion's nitrate. So we just covered nitrate. That's neutral. Yeah, iron 3 plus. Weakly acidic because it's a small, highly charged cation. So this is weakly acidic. Or we'll just say acidic because we're not being that specific. Cool. Not so bad. Actually, any questions? Relevant questions can also earn a Jolly Rancher.
Relevant questions.
How many Jolly Ranchers do you want? I know, and there's been some times where a bunch of people answer, and I'm not going to try and throw Jolly Ranchers to everyone. Which ionic compound forms an acidic solution when dissolved in water? Huh? Yeah. NH4 plus, Br minus, this will be a weak acid. K plus is neutral. Cl minus is neutral. Br minus is neutral. Na plus is neutral. HCO3 minus, weak base, because it's the conjugate of a weak acid. So it is A. What flavor do you want?
Grapefruit.
I'm gonna get so good at tossing small things. Yeah. Oh, we didn't even get to, well, we got time now. That's fine. Can you get to polyprotic acids? I guess we have time to introduce it. Are there questions so far? No? So let's just take a look at polyprotic acids because I think it makes a lot of sense if you kind of been at least mostly or at least partly understanding everything that we've been talking about so far in terms of equilibrium. So our polyprotic acids, unlike, they don't call them polyhydroxic bases. So something like calcium hydroxide, a strong base that's got two hydroxides, those leave at the same time. You put that in water, they just leave. These ionize in steps. And so here, this is not sulfuric acid, it's sulfurous acid. You see that the first step here leaves, our hydrogen leaves, and that has a K value. And then I have another equation for HSO3 minus, and that has its own K value, which is a lot smaller. The other thing to think about is, so when this first one ionizes, right, we could do a whole lyse table, calculate the whole thing, but does this K favor reactants or products?
The second one.
K1, Ka1. Reactants or products? Reactants. Reactants. I'll just there's a lot of jelly ranchers throughout. So if you feel like you've earned a Jolly Rancher, but I didn't toss you one, you can come up and get a Jolly Rancher after. I have enough. Honor system. Honor system. So we're gonna devalue the Jolly Rancher. It's gonna be too many. Flood the economy. So this favors the reactants, which means that there's not going to be a lot of products. And the product that I'm sort of leading into here is this is HSO3 minus, which is what goes here. So not only is this K, Ka2, smaller, a lot smaller, but that Ka2 only applies to the small amount of HSO3 minus that gets made in the first step, which is already going to be pretty small. So most of the time, we can ignore the ionization of the second proton. There just won't be enough of it because there's going to be already a small amount of, it would be bisulfite, hydrogen sulfite. There's already going to be a small amount of that. So that means that with this even smaller K, there's going to be even smaller amounts of hydrogen produced and of the sulfite. So like in a table, you'll get Ks that represent all of the different protons that could leave. So like phosphoric acid has 3. And 7.5 times 10 to the minus 3 is still a weak acid, but like respectable K1. But then Ka2 is 10 to the minus 8. Ka3 is 10 to the minus 13. And at every step of ionization, the amount of phosphoric acid that gets turned into, but like H2PO3 minus, PO4 minus, is already going to be a small amount. And then that's going to be a small amount that ionizes a tiny amount. And that'll be a small amount that ionizes an even tinier amount. The only one that we can't just kind of completely ignore is sulfuric acid. And for sulfuric acid, it kind of like acts like having a strong acid like hydrochloric acid and then adding a weak acid to it. Because its first hydrogen is strong, ionizes completely. The second hydrogen then we treat like a weak acid, but there's already H plus in solution from it ionizing the first time. But it's got a fairly large K for even that second hydrogen. So because our first K is so large, produces H3O plus, which is going to be in the products of every reaction after that, it even suppresses that further. So there are already small K values. The amount that gets, or then that's suppressed, so almost nothing actually gets ionized. Not to say that nothing gets ionized, but almost nothing. All right, so we'll do examples of that and probably finish out this chapter on Friday.